In this video, we learn about determination of hybrid pi conductances. Determination of hybrid pi conductances. Determination of hybrid pi conductances. First one is transconductance. Transconductance. It is represented by GM. Transconductance is nothing but the ratio of current to voltage. Transconductance. For the determination of transconductance, let us consider PNP transistor in the CE configuration with VCC bias. This is the PNP transistor. PNP transistor in CE configuration. This is the emitter, base, collector with VCC bias in the collector circuit. This is the VCC. P is connected to negative. This one is positive. Minus plus VCC. This one is some resistance RBB dash. This one is B dash. Virtual base terminal is this B is the physical base terminal. One is emitter. Common emitter configuration. Emitter base junction is forward bias and collector base junction is reverse bias. Reverse bias means P is connected to negative of that VCC. Transconductance. Suppose a small voltage here. This one is VB dash E. VB dash E here. This one is VE. This one is VE plus minus. The transconductance is nothing but the ratio of change in collector current. Ratio of change in collector current due to small change in the voltage VB dash E. This one is GM is equal to ratio of small change in collector current, that is dou IC by ratio of the change in collector current, not change in collector current, dou IC due to small change in the voltage. Small change in the voltage is dou VB dash E across the emitter junction by keeping a VCE constant. For PNP transistor, the collector current in the active region is given as the collector current in the active region. In the active region is given as IC is equal to IC naught alpha into IE. And GM is equal to dou IC by dou VB dash E. Dou by dou VB dash E, That is IC naught minus alpha IE. IC naught is constant minus alpha into dou IE by dou VP dash E. That is equal to minus alpha dou IE by VB dash E is equal to minus VE from this figure. Forward bias means here plus and this one is negative, this one is positive. VB dash E is equal to minus V. VB dash E is equal to minus VE. Dou of minus VE. That is equal to alpha into dou IE by dou VE. That is GM, transconductance GM. Suppose diode is nothing, transistor is nothing but two diodes connected back to back. Emitter base junction is forward bias. Therefore, one diode is under forward bias condition. Collector base junction is in reverse bias condition. That means another diode is under a reverse bias condition. Therefore, we have to exhibit some emitter diode resistance that is given by emitter diode resistance. Emitter diode resistance RE is equal to input current, input voltage dou VE by dou IE. Dou VE by dou IE. Therefore, this value is substituted in this one. Above equation, GM is equal to alpha into dou IE by dou VE is equal to 1 by RE. That is equal to alpha by RE. Alpha by RE. The emitter diode is forward biased diode and dynamic resistance is given by dynamic resistance. Dynamic resistance of the forward biased emitter diode is, that is equal to RE is equal to general formula VTE by I. Emitter current is I. VTE by VT by RE. Therefore, VT is equal to KT by Q into I. GM is equal to, we know that GM is equal to alpha by RE. From this expression, alpha by RE is equal to KT by Q into IE. That is equal to alpha IE by here IE KT by QE. Therefore, alpha E by KT by Q. We know that IC is equal to IC naught minus alpha IE. Alpha E is equal to IC naught minus IC. Therefore, alpha IE is equal to IC naught minus IC by KT by Q is let it be Generally VT, KT by Q is VT. Write down here. For a PNP transistor, IC is negative. IC is negative. For NPN transistor, IC is positive. Initially, we consider a transistor is in a PNP configuration. For a PNP transistor, IC is negative. IC is negative. For NPN transistor, IC is positive. Therefore, for the foregoing analysis, with VE is equal to plus VBE for NPN transistor. Therefore, GM is equal to, for NPN transistor, IC is positive, IC minus IC naught by VT. Therefore, GM is equal to IC is greater than IC is far greater than IC naught. Reverse saturation, this is due to IC naught is due to minority charge carriers. IC is due to majority charge carriers. Therefore, IC is far greater than IC naught. IC naught is neglected. That is equal to IC by VT. VT is equal to KT by Q. We know that Q value IC into Q by KT. IC into Q is 1.6 into 10 power minus 19. K is Boltzmann constant, 1.38 into 10 power minus 23 into T. That is equal to IC (11,600 by T). 11,600 by T. At room temperature, that is 20 degrees centigrade, small t is equal to 27 degrees centigrade, capital T is equal to 27 degrees centigrade plus 273 is equal to 300 degree Kelvin. This value is also substituted here. Therefore, GM is equal to 11,600 into IC by 300. That is equal to IC by 26. Therefore, IC is in milliamps. See the transconductance. GM is equal to this value. This is the GM. Or GM is equal to IC by VT. Next one is input conductance. The input conductance, that is GB dash. Generally, for a determination of input conductance, we need to consider H parameter model for CE configuration at low frequency, hybrid pi model for CE configuration at low frequency. Two models are considered for the determination of input conductance. First one is a hybrid pi model. For CE configuration. At low frequency. Second one is H parameter H parameter model for CE configuration. For CE configuration at low frequency. Consider these two models, and we have to make some assumptions. Determine the input conductance GB dash E. First model is a hybrid pi model. This one is a hybrid pi model. RB dash E. This one is base current IB, VB dash E, RB dash C, GM into VB dash E, GM into VB dash E. This one is RCE. One is emitter. CE, here the CE capacitance and the CC capacitance are there in hybrid pi model. These two capacitance values are neglected at low frequency. At low frequency, because hybrid pi model for CE configuration at low frequency. This is the hybrid pi model for CE configuration at low frequency. But low frequencies, these two capacitive effects are neglected. CE and CC. That is the reason CE and the CC are eliminated. This is the RB dash E due to forward bias is applied at the emitter base junction. Therefore, set VCE is equal to 0. Set VCE is equal to 0. That means shorted. VCE is equal to 0 means short circuited. RCE, due to short circuit, RCE is also 0. This is short collector current IC. IC is equal to GM into VB dash E. IC is equal to GM into VB dash E. But this IB current flow through RBB dash and RB dash E, not flow through RB dash C, because RB dash C is high value 4 mega ohms. Current flow is towards the low resistance path only, not high resistance path. That is the reason this IB current is not a flow through this RB dash C. Current is not divided at this point. Therefore, VB dash E is equal to VB dash E is equal to IB into RB dash E. IB into RB dash E. Therefore, IC is equal to GM into VB dash E is substituted here. VB dash E is IB into RB dash E. IC by IB. IC by IB is equal to GM into RB dash. RB dash. This is the equation. First model is completed. Second model. This is the first model. Second model, H parameter model for CE configuration at low frequency. Second model is a H parameter model. This one is HIE, HRE, VCE, base emitter. This one is VI, base current is IP, one is emitter. HFE, IB, HOE, I2, CE. Again, like a previous case, set VCE is equal to 0. VCE is equal to 0 means that is shorted at this. Apply nodal analysis here. I2 is equal to, or IC. This one is IC. IC is equal to, this is the voltage. Suppose it is not shorted. The voltage across this one is VCE. VCE. Therefore, IC is equal to HOE into VCE plus HFE IB. Put VC is equal to 0 in this equation. Put VC is equal to 0 in this equation. IC is equal to HOE into 0 plus HFE IB. Therefore, HFE is equal to IC by IB. This one is equation 2. See the in the first case, by using hybrid pi model, IC by IB is equal to GM into RB dash E. By using H parameter model at a low frequency, both models are at low frequencies. Therefore, from first equation, HFE is equal to GM into RB dash. IC by IB. IC by IB. IC by IB is equal to GM into RB dash from equation 1. Equation 1. But IC by IB is equal to HFE. HFE is equal to GM into RB dash E. But RB dash E is equal to HFE by GM. HFE by GM. But we need to calculate the input conductance is GB dash E, that is 1 by RB dash E. 1 by RB dash E is HFE by GM. Therefore, GM by HFE. GM by HFE, that is GB dash E. GM is equal to, we know that GM is equal to IC by HFE. IC by VT HFE. This is the GB dash E. The input conductance. This is the input conductance GB dash E. Next one is feedback conductance. Third parameter is the feedback conductance. The feedback conductance GB dash E. In order to calculate the feedback conductance GB dash C, set IB is equal to, in the both models, hybrid pi model for CE configuration at low frequency and H parameter model for CE configuration at low frequency. Why IB is equal to 0? Because GB dash C or RB dash C is due to reverse bias across the collector base junction. That is the reason put IB equal to 0. We will concentrate on output circuit only. At that instant, put IB equal to 0. The analysis is from right to left. The analysis is from right to left. Consider hybrid pi model for CE configuration at low frequency, that is here. RBB dash. This one is base. RB dash E. One is emitter. VB dash E. RB dash C. GM into VB dash E. GM into VB dash E. This one is RC. IC. C. E. That is VC. Here IB is equal to 0. IB is equal to 0 means the drop across RBB dash is 0. Next one is find out. This is the VCE. This is the RC and the GMBB dash E is conductor parallel. The voltage across both these branches is equal to VCE. The analysis is from right to left. Okay, now VB dash E, calculate VB dash E is equal to total voltage applied to the circuit is VC into this one, this resistance RB dash E by sum of these two resistances RB dash E plus RB dash C. Here VC is the voltage across RC. VC is also voltage across this current source. Therefore, finally VB dash E is the total voltage applied to the circuit is VCE into VB dash E is the voltage across RB dash E. That is the reason multiply RB dash E by sum of these two RB dash E plus RB dash C. Here VI, here VI. VB dash E is VI because IB is equal to 0. The drop across RBB dash is also 0. VI is equal to, since VI is equal to VB dash E. Therefore, VB dash E is equal to VI VCE into RB dash E by RB dash E plus RB dash C. This is the equation 1. Consider H parameter model at low frequency. This one is HIE. Put IB equal to 0. IB equal to 0. HRE, not this one is resistance. Plus minus HRE, VCE. This one is HFE, IB, HOE, collector emitter. This one is a base emitter. IB, this one is a IC. One is VI. IB equal to 0 means the drop across HI is also 0. Therefore, VI is equal to HRE, VC. This is the equation number 2. Equating these two, 1 is equal to 2, VI is equal to HRE into VCE. VA is equal to HRE into VCE is equal to VCE RB dash E by RB dash E plus RB dash C. VCE cancel to each other. Therefore, finally find out RB dash C. Cross multiplication. RB dash E is equal to HRE RB dash E plus HRE RB dash C. HRE RB dash E is equal to HRE RB dash E minus RB dash E. Therefore, RB dash E is equal to HRE minus 1. HRE minus 1 or 1 minus HRE. HRE into HRE VCE RB dash E VCE by RB dash C plus RB dash E. RB dash E HRE RB dash C HRE, that is equal to RB dash E. Here I committed some mistake here. Therefore, RB dash E minus HRE, RB dash E, HRE, RB dash C. This one is RB dash E into 1 minus HRE by HRE into RB dash C. From that expression, RB dash C is equal to RB dash E into 1 minus HRE by HRE. 1 minus HRE is approximately equal to 1. Therefore, RB dash E by HRE. RB dash E by HRE. Conductance means GB dash C is equal to HRE by reverse RB dash E. HRE by RB dash E is equal to, from that initial, RB dash E is equal to HFE by GM. HFE by GM. This is GM. GM is equal to IC by VT. IC by VT. Therefore, GB dash C is equal to HRE by HFE into IC by VT means KT by Q. This is the feedback conductance. Feedback conductance. Next, third one is fourth one. The base spreading resistance. The base spreading. The base spreading resistance. RBB dash. The base spreading resistance is RBB dash. This is for including at the input side. They put VC is equal to 0. VC is equal to 0. Consider both these models. First model is RBB dash IB, RB dash E, BB dash E. One is B dash emitter, some feedback resistance RB dash E. This is GM into BB dash E, RCE. This one is IC, VCE. Put VC is equal to 0. VC is equal to 0. VC is equal to 0. VC is equal to 0 in the hybrid model. Let us consider H parameter model C configuration. Find out the input resistance Ri. Input resistance Ri is equal to VC is equal to 0 means RC is equal to 0. This IB current not flow through this RB dash C because RB dash C is high resistance value 4 mega ohms. Current is not flow through towards the high resistance value. Therefore, Ri is equal to, this one is VI by IB. VI by IB. But VI is equal to IB into RBB dash plus RB dash. These two are connected in series. From this expression, VI by IB, that is R, is equal to RBB dash plus RB dash E. This is from hybrid pi model, and consider H parameter model. HIE, IB, HRE, VCE, base, emitter, HFE, IB, HOE. This one is IC, the emitter, VCE. Put VC is equal to 0. VC is equal to 0 means put VC is equal to 0. This value is also HRE into 0 is 0. This is shorted. Therefore, RI is equal to this is VI by IB. VI by IB. But VI is equal to IB into HI. VI by IB is equal to HI. This is the equation 1. This one is equation 2. 1 equal to VI by IB is HI. Substituted here. HI is equal to RBB dash plus RB dash E. Therefore, base flooding resistance RBB dash is equal to HIE minus RB dash E. RB dash E is equal to GM by, we know that RB dash E is equal to already derived HFE by GM. HFE by GM. HFE by GM. Therefore, RBB dash is equal to HIE minus GM is equal to IC by VT. IC by VT. This is the base spreading from physical base to virtual base. Next, coming to last parameter, the output conductance. The output conductance, that is the fifth one. The output conductance. GCE. The output conductance is GCE. Consider hybrid pi model at low frequencies. Again, hybrid model at low frequencies. This one is RBB dash, IB. This one is base, B dash. This one is VB dash E, emitter, RB dash E, some feedback resistance RB dash C. This one is GM into VB dash E, RCE. This one is collector current. This one is VC. With the collector terminal. IB is consider output portion only. For output conductance RC, output resistance RCE, conductance GC is equal to 1 by RCE. Consider output portion to this up to this point only. This is the current I1. This is the current I2. Therefore, IC is equal to current entering into the node I1 plus GM VB dash E plus 8. But I1 is equal to VCE by RCE. I1 is equal to VCE by RCE. GM into VB dash E. GM into VB dash E plus I2. Therefore, IC is equal to VCE by RCE GM into, but VB dash E is equal to VB dash E is equal to RB dash E into VCE. Here VCE is same, VCE into RB dash E by RB dash E plus RB dash E. GM into VB dash E is equal to RB dash E into VB dash E by RB dash E plus RB dash C. And one more expression is also there. That is I1. I1 is equal to I1 is equal to here. These two are connected in series. Here voltage is VCE. From that VCE only I2 current is obtained. Therefore, I2 is equal to VCE by sum of these two resistances. Because IB is not flow towards RB dash because RB dash is high value. IB is the loop current only, not divided at this point. Therefore, I2 is equal to VCE by RB dash C, RB dash E. I2. For the determination of output conductance, put IB equal to 0. IB equal to 0. That is equal to IC is equal to VCE by RCE plus GM into, here common term is here VCE. Total voltage applied to the circuit is VCE. In all the here VC is there, here VC and VCE. Common term ICE by VC 1 by RCE GM into RB dash E by RB dash E plus RB dash C plus 1 by RB dash C plus RB dash E. Therefore, 1 by RCE GM into RB dash E is HFE. RB dash E, RB dash C, RB dash C, RB dash E is the common one. Therefore, RB dash E plus RB dash C is equal to IC by VCE. 1 by RCE, HFE plus 1. HFE is equal to 100. 100 plus 1 is 1 at 1 is approximately equal to 100. HFE by RB dash E plus RB dash E. HFE is greater than far greater than 1. This is the IC by VCE. This is equation 1 from hybrid pi model. For H parameter model, from this H parameter model, HIE, IB, base, HRE, VCE, HFE, IB, this one is emitter. Admittance is HOE, CE, VCE. This one is VI. IB equal to 0. This one is IB equal to 0. Therefore, from this one, HOE is the admittance. IB equal to 0 means HFE IB is open circuited. Therefore, HY is equal to admittance, HY is equal to current by collector current by IC by VC. But here IC by VC is HY. Finally, HOE is equal to 1 by RCE plus HFE by RB dash C plus RB dash E. HOE is equal to 1 by RCE. RB dash is 1 kilo ohm. RB dash is 4 mega ohms. Therefore, 1 kilo ohm is neglected compared to this one. HFE by RB dash C is present. Next step is calculate RCE. HOE is equal to 1 by RCE is GCE. HFE into 1 by RB dash is GB dash C. Therefore, GCE is equal to HOE minus HFE GB dash. GC is nothing but conductance, output conductance. It is also called as 1 by RC. These are the derivations. Conductance, hybrid pi conductance. First one is GM, that is IC by VT. Second one is RB dash E is equal to HFE by GM. Third one is HIE is equal to RBB dash plus RB dash E. Fourth one is RB dash C is equal to RB dash E by HRE. RB dash C by HRE. Fifth one GCE is equal to 1 by RCE is equal to HOE minus GB dash C HFE. These are the important parameters. Relation between hybrid pi and H parameters. This is the relation between hybrid and hybrid pi and H parameters.